about positional embeddings, right? So we call them positional encodings or positional embeddings. So when we saw recurrent neural networks natively had the potential to calculate the relative position because we were moving in one direction, left to right, and we were moving with tightly dependent sequences t0, t1, t2, t3, t4, right, at time instance 0, time instance 1, time instance 2, and so on. Here, our neural network or our transformer does not natively store positions, right? So we need to have a different vector, one vector for the meaning of tokens, which is token embeddings, one vector for the positions of tokens, which is positional embeddings or positional encodings, right? So we have to synthetically generate or store positional embeddings. Even if we talk about the attention formula, right? So let's say transformer is based on one crucial thing, which is attention. The input to attention is embeddings, right? Even if we look at attention formula produces something known as contextual representation between token I and token j, right? Even that attention formula does not natively take into account or computes positional embeddings. It also relies on the input, right? So at the input end only, we need to have something known as positional embeddings. If you look at any architecture, so input token vectors, let's assume that this means as input embeddings or token embeddings is always added with something known as positional embeddings, right? You look at any architecture, right? So in case of attention is all you need, the original transformer that we described, which is the encoder decoder transformer, right? They use something known as sinusoidal, positional embeddings. They are static. They are generated and then frozen. They are not learned. They are not trainable. In case of attention is all you need, right? So whenever we talk about transformers, we discussed more or less three architectures. Attention is all you need. Decoder only transformer, which is your GPT family. Then BERT family, right? Which is encoder only. Now the attention is all you need. The original paper in 2007, which says attention is all you need, proposed an idea of positional embeddings, which is using sinusoidal waves, right? To compute positional embeddings, and then they have some formula with which they simulate the positions, and the original transformer paper uses fixed sinusoidal functions to encode the positions of each token, right? These are mathematical waves of different frequencies added to each embedding dimension. Now embedding dimension stays similar to what we had in token dimensions or token embedding dimension, right? So let's say if token embedding is a 512 dimension vector, positional embedding for that particular token is also going to be 512 dimension, right? For example, here we can see that the to decode or to encode the position of the, which is 0th position, we have this particular embedding. Then to encode the position of cat, we have this particular embedding. Then sat, we have this particular embedding, right? Now, what exactly is different in case of GPT, right? So this is the GPT-2 paper, right, which we are going to reproduce in one of our courses. So GPT-2 paper, when they talk about this is the title of the paper. Language models are unsupervised multitask learners. Okay, so when they talk about the model that they use, they simply mention that we use a transformer, which is attention is all you need, Baswani et al. So this is the attention is all you need paper based architecture for our language models. The model largely follows the details of the OpenAI GPT model, which is mentioned in this paper. So if I go to this particular paper, right, which is mentioned here, I will be able to see something which clearly states that we used learned position embeddings instead of the sinusoidal version proposed in the original book, right? So that we can simply say that although they both are transformers, one transformer architecture says I will use fixed sinusoidal waves to encode my positions. One transformer architecture says that I will use learned position embeddings instead of sinusoidal version proposed in the original attention is all you need paper, right? So if we, even if you look at the code, right? So this is the GPT-2 code in their own official repo, which is the GPT-2 repo by OpenAI. They are trying to generate this, they are trying to create a parameter matrix called as WPE, which stores positions. Now WPE basically is a matrix that belongs to a set of real numbers of size, context length or sequence length or input sequence window, whatever you call it, multiplied by embedding dimension or decay, right? So this can be the size. Let me show you. Yeah, so yeah, this is how we will describe our positional embedding. So this is also one way that you can initialize your positional embedding vector. So I think enough about positional embeddings. We have seen two dimensions. One is the GPT-2 version of positional embeddings, and then the other is the attention is all you need version of positional embeddings. The only thing that we need to understand is no matter whatever version we are using, we need to add both of them, right? Let's say this is called as embedding vector E, and this is called as embedding vector P. E plus P will make something known as Z, or whatever you can name it, and that is going to be the output or to the attention block, right? So let's revisit it again. Let's say this is the token embeddings, this is the positional embeddings. We add both of these vectors, and the addition is going to be on matrices, which is going to be element wise addition, and then this is going to act as the input to the attention block, or input to the multi-head attention block, or the attention sublayer, whatever we can call it, right? I'll see you in the next video.